the last result we covered is called the Net Change Theorem. And the Net Change Theorem is a rephrasing of the second part of the a rephrasing and a reinterpretation, I should say, of the second part of the fundamental theorem of calculus for when the derivative is specifically measuring some rate of change. So here, when a quantity is changing, the new value equals the initial value plus the integral of the rate of change of that quantity. And notationally, capital F of B equals capital F of A plus integral from A to B of the rate of change. So we're integrating a rate of change. And we'll look at 3 examples. The first one is just to illustrate the net change theorem, and the next 2 will be more specific examples in interpreting it. A honeybee population starts with 100 bees and increases at a rate of n prime of t bees per week. What does 100 plus integral from 0 to 15 n prime of t dt represent? Well, this tells us if we start at an initial value and integrate a rate of change on some interval, starting at that initial value, then that will give us a new value. So this, after we're integrating from 0 to 15, what are our units? Per week. So this represents the number of honeybees in whatever column in the population after 15 weeks. So we start at 100 and we integrate from 0 to 15. We integrate the rate of change. That'll give us a new value, and it'll be the total number of honeybees after 15 weeks. Next, a car moves due north. And when we're talking about velocity, you're going to have to specify which direction is a positive direction. I mean, the computation will be the same even if you, right here I say north is the positive direction and down here south is the negative direction. If you said south was the positive, north was the negative, you'd get the same answer. You just have to interpret a negative sign a little differently. But here we're going to define moving north as positive, moving south as negative. Car moves due north at 40 miles per hour between 2 and 4 p.m. Okay? And it moves due south at 30 miles per hour between 4 and 5 p.m. 2 things. Find the net displacement and find the total distance traveled. Well, with this example, you can probably answer both of them without knowing any calculus. Car moves north 40 miles per hour for 2 hours. So it goes 80 miles north. Then it moves south 30 miles per hour for 1 hour. So it goes 30 miles south. So you go 80 miles, 30 miles. So overall, you've moved 50 miles from your initial point. That would be the net displacement. Total distance traveled would be 80 plus 30, 110. But we can interpret this using calculus. So let's interpret this using calculus. We can use the net change theorem, because this 40 miles per hour, 30 miles per hour, those are just rates of change. So how can we do this using the net change theorem? Well, how can we do the net displacement using the net change theorem? So net displacement. Well, for this, we can assume we're at position 0 at 2 p.m., meaning we can assume we're at position 0 here. So net displacement, integral of our rate of change, which I'll call, there's no notation for a velocity function in our question, but it is a velocity function that we're thinking of. So I'm going to just call it v of t. We're integrating from 2 to 5. But notice, on this interval 2 to 5, something happens from 2 to 4, and something else happens from 2 to 5. So what we're going to have to do is split this integral into something on 2 to 4 and something on 4 to 5, because we have different velocities on those 2 intervals. What happens on 2 to 4? Well, it moves north, the positive direction, at 40 miles per hour. So the velocity is 40. What about from 4 to 5? What happens? Well, it goes south, which remember is the negative direction. So the velocity is going to be negative. So minus 30, which is the velocity, negative 30. So plus negative 30 or just minus the integral 30 from 4 to 5. Well, now we just have to do these integrals. That's easy enough. Integral of 40, antiderivative of 40 is 40t from 2 to 4 minus antiderivative of 30 is 30t from 4 to 5. And what do we get here? 40 times 4 is 160. I guess I'll write that out. 40 times 2 is 80. So we get 160 minus 80 minus, yeah, I think I'll be able to fit that in. 30 times 5 is 150. 30 times 4 is 120. So we have 40 times 4 minus 40 times 2 minus 30 times 5 minus 30 times 4. And what do we get? We get 80 minus 30, which is 50. As we said, this marker's running out. So we found the net displacement. And let's look at this integral a little. This integral, remember, the definite integral is going to treat this as a negative. In figuring out the net displacement, when you go backwards, that counts against it, against the distance in consideration, I should say. But for total distance traveled, when you're walking backwards, that's still contributing to the total distance traveled. In other words, this negative portion, as far as total distance travel is concerned, is going to be a positive quantity. Because if you walk backwards, you're still walking if you're trying to figure out a total distance traveled. So let's find total distance traveled. Traveled is 1L in America. How can we've seen how to make a negative a positive. How can we turn a negative into a, well, maybe not turn into a, what can we do to a function to treat its positive quantities as positive and treat its negative quantities as positives as well? Well, we can do that. That's not 4. We can do that by considering an absolute value. The absolute value will take those negatives and make them positive. It'll take positives and leave them positive. So we have the integral of the absolute. We haven't integrated an absolute value function. How do you do that? Well, to integrate an absolute value function, you still have to split it into the pieces. If it's an absolute value like this, you have to split it into this piece and that piece. In this case, it still splits at 4 because the velocity changes at 4. So what would this integral equal? Well, it would equal integral from 2 to 4. What's the absolute value of velocity from 2 to 4? Well, it's the absolute value of positive 40, which is just 40. Plus the integral from 4 to 5. The velocity from 4 to 5 is negative 30. The absolute value of negative 30 is 30. So the absolute value takes the negative pieces and interprets them as positive. Well, it makes them positive. Well, now if you do this integral, you again get 40t from 2 to 4, which is 80, plus 30t from 4 to 5, which is 30. So you do get 110, as we saw. Now this velocity, or these integrals, it might be useful to see what the graph of the velocity function looks like. So let's look at the graph of the velocity function. Now right here on the third board is a graph of the velocity function from the previous example. From 2 to 4, so the x-axis has time, the y-axis has velocity. So from 2 to 4, the velocity was 40. From 4 to 5, the velocity was negative 30. And what we were doing when finding the net displacement was really finding, for the net displacement, finding that area and subtracting that area. And of course, these are rectangles, so you didn't even need an integral to find the area. And sometimes you can find the shapes without going through an integral. And the net displacement treated this as a negative because you were going in the backwards direction. But the total distance traveled didn't do that. The total distance traveled said, well, this is distance traveled, this is also distance traveled. We're going to add those two areas together. And one way of doing that using an integral is by taking this function and moving it into the positive, moving it into the positive section. So flipping it over the x-axis, and you can do that by taking an absolute value. Let's look at one more example. And we'll see one of the computations for this example is kind of a pain. Especially if you don't just consider the graph, which we won't for this one. Although you could if you want. Given velocity, v of t is 3t minus 5. Okay, find the net displacement and the total distance traveled from t equals 0 to t equals 3. Okay, let's do net displacement first. Well, net displacement, remember, treats areas above the x-axis as positive, areas below the x-axis as negative. So we can just use an integral of our velocity function from 0 to 3, because this one says 0 to 3. Integral of velocity from 0 to 3 will give us net displacement. Well, how do we do this? Well, we get a half t squared times 3, so 3 halves t squared, minus 5t from 0 to 3. Well, evaluate at 3, you get 27 halves minus 15. Evaluate at 0, you get 0 minus 0. So 27 halves minus 30 halves is negative 3 halves is our net displacement. So from 0 to 3, whatever this velocity function is measuring, whatever the velocity function is measuring the movement of, goes back 3 halves of a unit. I didn't throw units in this question. Well, that's great. What about total distance traveled? Well, we're going to see that this computation is a real pain using an integral. Total distance traveled. Well, remember, to do this, we're going to consider walking backwards as a positive. So we're going to need to integrate the absolute value of our velocity function from 0 to 3. How do you integrate an absolute value? Well, what is 3t minus 5? 3t minus 5 is a line. Well, if we're going to integrate an absolute value function and we have a piece below the x-axis and a piece above the x-axis, well, what we need to do is figure out what piece is below the x-axis and what piece is above the x-axis. And we're going to split this absolute value function at that point. And my pen is... No, these are all running out of ink. Let's see if this one has any left. Pen, marker. And we want to find this value. Well, how do we find where a function intersects the x-axis? Well, what happens at this point? It goes over something and up 0. So the y value is 0. So 0 equals 3t minus 5. Solve for t, what do you get? T is 5/3. Add 5, divide by 3. Well, that tells us some of the information we need. Let's write it down. So this integral equals, it splits at 5/3. We have not taken an absolute value yet. all we did was figure out where the absolute value changes from negative to positive. How do we take an absolute value? Well, how do we take an absolute value? What's negative becomes positive. What's positive stays the same. So what we need to do is look at this function on this interval. A couple of ways you could do that. Here's one way. I mean, we know what this looks like because I just drew the line. But suppose you didn't know what it looked like. All you know is that it goes through the point 5/3 0. Well, what you could do is pick a point here. Say 1. And if 3t minus 5 is positive, well then the absolute value is itself. If 3t minus 5 at 1 is negative, well then you have to take the negative of everything. So 3t minus 5, I'm going to write it over here. T minus 5 at 1 is negative 2. So it's negative. So that tells us on 0 to 5/3, this line, 3t minus 5, is below the x-axis. So that means the absolute value is the negative of the inside. So the absolute value of 3t minus 5 on 0 to 5/3 is negative 3t plus 5, also known as 5 minus 3t. Plus integral from 5/3 to 3. Now we know because it's a line, if this piece is negative, the other piece is positive. But how would you be sure it's positive? Well, you take a point between 5/3 and 3, say 2, throw it in here, and you need to get a positive. Between 5/3 and 3, choose 2. If t equals 2, you get 6 minus 5, which is positive 1. So the absolute value is itself. Well, now we just have a bunch of power rules and substitution. So let's do that. 5 minus 3t, we get an antiderivative is 5t minus 3 halves t squared. And we're evaluating from 0 to 5/3 plus 3 halves t squared minus 5t, and we're evaluating that from 5/3 to 3. Oh, that's nice. 5, substitute 5/3, you get 25/3. Substitute 5/3 here, what do you get? 25/9 times 3 halves. 25/9 times 3 halves puts a 6 in the bottom. And what, a 50 on top. Does it? 25, I forgot my numbers. I guess I have to write it down. 3 halves times 25/9. Yeah, okay, so that's a 3, that's a 1. So yeah, I did forget my numbers. So we get a 6 on the bottom and a 25 on top. Substitute 0, you get 0 minus 0, so that's nice. The other one, it's not gonna be as nice. 3 halves times 3 squared is 27 halves. Minus 5t, so minus 15. Then we have to subtract. What happens when we evaluate at 5/3? Well, again, we're gonna get 25/9 here, or 25/6 here. Because it's 3 halves times 25/9, but it's positive this time, whereas negative that time. Minus 25/3. Now we have some addition to deal with. What addition will we do? I'm going to combine these two first. That's a negative 3 halves. And then what do we have? 25/3 minus negative 25/3. 25/3 plus 25/3. That's 50/3. And the other thing, negative 25 sixths minus 25 sixths. What does that give us? Negative 50 sixths. So negative 25 thirds. Well, what do we get here? Did I do something wrong? No, okay. Let me just make sure I didn't do anything wrong. Yeah, okay, that's good. So negative 3/2 I'm going to carry along, because these two combine into 25 sixths. I'm going to write that backwards. 25 thirds. So the negative's in the middle. 50 thirds minus 25 thirds is 25 thirds. Negative 3/2 goes along. And then you add these together. What do you get? 50 minus 9 over 6. 41 sixths. So integrating an absolute value function is not easy, because you need to figure out where it intersects the x-axis and split it there, but then you also need to figure out where it's positive and where it's negative. So try a computation like this and see how it goes. It's not, well, it's very easy to mess up a number here, but now make sure you set up the integral right, split the absolute value, and see how it goes from there.